Yeah, and we're live. So this is the algorithms mob, and man, so that, yeah, hopefully, yeah, we're gonna be wrapping up Haskell this week, and we'll work on the map coloring problem at the end of this section, and and then the next time we meet, we'll get back into the algorithms book. So just to recap, last week we were working on generating lists. We can break the list into like head and tail. So that was deconstructing a list. But I'm going to silence your mic, okay? Let's see. There we go. All right. So last week we worked on deconstructing a list into heads and tails. And then we can also use that notation to construct a list also. And here we added so here we can do one colon. We can add a list to a number. We can add a number to a list. We can add a list to a list of lists. Yeah. So we're adding this list here to a list of lists, but we can't add a list to a list. But we can add it to a list of lists, which makes sense, I guess, if you think about it. You can add a number to a list of numbers. And we saw how we could write a simple program to find out all the even numbers in a list. And then we worked with ranges and composition. So pretty much the same in Ruby. You can do a range with the dot, which is, I guess, basically syntactic sugar in Haskell. And looks like it does it inclusively. So 1.4 lists all the numbers 1 to 4 inclusive. And then we did this last week, right? Yeah, we did. And then and we saw that we can, well, specify an incrementation. So we could say, okay, well, we'll start with 10, and then we'll decrease by 2 and go all the way down to 4. Do it with floating points also. And then yeah, so let's cover list comprehension, and then that's it. Just like 2 pages, and we're done with this section. So, oh yeah, we're using Cloud9 in this. So got to get that started. Here we go. I'll post the link for you in the chat there, okay, if you want to log in. And so we'll get started. Let's see. So we'll need let's just use the terminal here. All right, so list comprehension. I guess in this book they covered it in in the Erlang chapter. I know Python also has list comprehension. It's a way to just build lists. So for instance, if we wanted to, let's take a look at this. So on the left side of the expression, on the left side, you'll see an expression. On the right side, you'll see generators and filters. All right, so here it's all encapsulated in the list syntax. And then we've got x times 2, so that's our expression. And then a straight bar in Haskell is kind of like a guard. And then so on the right side, we'll see generators and filters. So here we're saying, so x is 1, 2, and 3. So this is a generator. So x times 2, where x is 1, 2, and 3. So then if we put in each of those values for x, we get 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and so it builds out that list there. All right. Do you want to give that a try in the terminal, Akoth? I see you're logged in, so I muted your mic in case you're trying to talk. I don't. All right. Well, are you there, Akoth? All right. Yeah, I guess I'll just type this out here. So GHCI. So we'll start off. So for list comprehension, syntax is open close brackets, and then inside there we need an expression. So we got x times 2, our guard clause. So where so this is where we want to say, well, x is going to have the numbers 1, 2, and 3. 2, 4, 6. So let's see. In English, the list comprehension means collect. All right, so collect x times 2, where x is taken from the list 1, 2, and 3. Cool. So that's pretty much, that makes good sense. So as with Erlang, I also use pattern matching with our lists. So we had a list of points representing a polygon and wanted to flip the polygon diagonally. You could just transpose x and y like this. All right, let's see. So, okay. So here's the syntax. So you got collect.
Okay, I tried typing it on the terminal. I'm seeing an error. I don't know why.
Oh, okay. I can't see your terminal. I wonder
why.
I don't know.
Okay.
Let me try opening up a new terminal here. Do you have access to this terminal here?
Let me try open it. Okay, I've opened a new one. Guys. Can you see my terminal now?
No. No. It's only showing that I have 2 terminals that I can view. You should be able to share the same terminal. Are you able to share your screen?
Okay, let me try that. Yeah. Okay, so how does it look?
Well, you need to go. So the first thing you need to do is go into the Glasgow Haskell compiler.
Oh, okay.
Interpreter. So GHCI.
Okay, CI.
Oh, GHCI. Yep.
Oh,
yeah.
Okay.
And now try it.
One, two. What?
So you got one thing missing. So after the guard bar, so collect x times 2, where we want to put an x in front of the that arrow. And I think it's just a dash. Is that an equal sign or a dash? Yeah, that looks good. Try that.
Okay.
Cool. All right, so let's do this next one here. So yeah, so we'll transpose x and y. So it's like x and y here is inside a tuple. So let's collect y and x, where then here we got it reversed. So x comma y, where it's 1 comma 2, then 2 comma 3, and then 3 comma 1. So it looks like it should be, yeah, it's going to flip all these around. So one's
Yeah, so it's reversing each.
One's going to assign to x, but then x is going to be on the other side. So it's going to basically be reversed. Each tuple will be reversed. That's what it does. So Yeah, I guess I already got GHCI open here. So we can say for our list comprehension, and then we got, I'm going to put X first here, X, Y, and then where, and we'll flip it around. Oops. Y comma X. We'll generate on the list of tuples. So it's arrow dash. So we need another list, and then inside that list is going to be a list of tuples. So we can say like 5 comma 6, 7 comma 8. And those should be flipped around to 6 comma 5 and 8 comma 7. There we go. Well, it's pretty neat, pretty useful stuff there. I don't know for what. To flip polygons horizontally, we could subtract x from 4 like this. So here we got, so here's our expression. So yeah, so we are,
Is that a 4 equals to x, or what's that? The first element in that.
in the first element, where?
Is it an assignment? Well, okay. Is it 4 equals to x? What am I saying? Okay, the first one.
This right here. So this,
Is it 4 equals x?
that's a subtraction sign. 4 minus x.
Oh.
Yeah,
Okay,
let me, should I increase the font a little bit? Or is that better?
I got small eyes. Yeah, it's better.
I don't know. I think sometimes it doesn't turn out too well. Like it might be it looks different on my screen than it looks on other screens. So
yeah, we're seeing 4 equals to x.
Okay. Yeah. So yeah, so here's our expression. So we got, so inside a tuple again, we got 4 minus x comma y. Then we're not doing any pattern matching here. We're just putting x right in the same position, except now will be, when this 1 comes over, it gets assigned to x. It's going to be put into there, so it'll be like 4 minus 1, which is 3. And then nothing happens to the 2. It's put into y, comes over here, it's in the same place, so there's our 2, and so forth. 2 and 3 get assigned to x and y, then that gets put over here, and then 4 minus 2 is 2, this will be 2 comma 3 right there, and so forth. 4 minus 3 is 1, so 1 comma 1. So yeah, did you want to try typing that out, Okoth?
Okay.
All right. Yeah, just share your screen again, I guess, if you can.
Now let's move on to what you be
Oh, it's a tuple. Okay.
You can use any numbers you want.
Oh, okay.
To, if you want to try something different, you don't have to copy the book exactly.
Let me try using 2 times instead.
This is an egg? What kind of egg is this?
So we have this, right? That's fine, right?
Yeah, that's fine. What will this generate for us when you hit enter?
Okay, this one will be x will be the first case. It'll be producing 2 times 2 times 3. No, 2 times 2. I mean, and then
That's
3. So that
you're right.
so
The first time it's 2 times 3
that will be
actually.
3 and 2 times 3.
Yeah,
2 times 3.
because 3 is in the X position, and then it gets pattern matched, or not pattern matched.
But I've switched. Okay, in the second position here, I've switched x with y. That is where I have x. So where there's y, I'll be expecting 3.
So
that will be 3 and 2. So that will be 4. 3 and 4. That is the first case. And then the other one will be 6 and 4 again. Okay, that's what I'm expecting, guys.
Okay.
Can I hit enter?
Yeah, go for it.
Wow. What happened?
So I think.
Okay, yeah. My multiplication was wrong. No. Yeah, I think so. 6 times 2 is 12. I understand.
Yeah, so so here the 3 in your first tuple gets bound to x, and then we're multiplying x times 2, so 2 times 3 is 6, which is what we got. And the 2, nothing happens to that, it gets bounced to y, and y is in the second position of our expression on the left side, so 6 comma 2. And then again, 6 times 2 is 12, so we get the 12, and then nothing happens to the 2. Yeah, and oh yeah, go ahead.
So it's switching x and y, that is in this case, because what I was expecting 3 times 3 to be 3, that is because 3's value is y,
Yeah.
and then I was expecting 2 to be 4, that is where
so
the second position should be 4 and 3 4, that is also value I was expecting for the first one. 3 4.
So how can we fix it so that we get what you were expecting?
Okay, we can switch the x and y in this position.
Okay, let's
in the field of it.
All right, let's do that.
No, it is.
Is that not what you were expecting?
Yeah, that is what I was expecting. Yeah.
Okay.
So,
Does it make sense then, or do you have
Yeah,
any
the
questions?
first one does. The second one does. The first one does not make sense. Why?
Okay. So in Haskell, when the assignment operator, it's not like an assignment in other languages. Like when we say like in other languages, when we go x is equal to 2, why is this not working? Oh yeah. See, it won't let me do x equals to 2, right? Do you know why?
Yeah. X equals to 2. Oh, it's okay. There's a immutability issue here.
What's that?
I think X is already pattern matched to a value, so it has a value. So it's like you're mutating it now.
Correct. In Haskell, you can't mutate variables. Once a variable gets assigned to something, they're bound. They use the word bound, so they get bound together. They cannot become undone. I can go z equals 2. Let's do something better here. Let's do a equals 2. Still didn't work. No, what's going on? All right.
Try a equals to.
Yeah, parser. I thought I could do this. Let's go.
But it's possible to. It's possible to. It's possible to assign, for instance, x is equal to 2, and then let us say a equals to 2.
Yeah, exactly. Yeah, I was hoping it would.
Yeah, it's possible. Reason is, I think a is just a pointer. Yeah? It's just pointing to a location in the memory. The 2 is where you cannot change the value of 2.
Oh, I got to use the word let. That's what I'm missing. Okay, let's try this again. So if we have that there. Okay, so if I say let a equals to 2, it works. We can say, what is a? It says 2. I say let a equal to 4, it still works. This is not what I was going for. But
so let's.
This is the fake hatchable. Clearly, look how all the packaging is.
Yeah. I think it's because we're in this interpreter. It might work. Probably works a little bit different using let and all that.
I know the difference, teacher.
But yeah. So, anyways, the point I was trying to make was that let's go back to this.
Comprehension.
Go back to the page we were on here.
I know everything. I'm the teacher.
All right, so here we are, list comprehensions. So the first example, we're going to do list comprehension and say, okay, so the values for x are going to be 1, 2, and 3. So insert those values here. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. So this was the first example where we had one variable. So these get assigned to x in that order, and it generates a list.
I get where my confusion was coming from.
Okay, cool.
Yeah, okay. The left-hand side. Okay, assuming from Do we call it pipe or do we call it?
Oh,
That the symbol between x, 2 and x, that is.
okay. It was hard to hear you. What was that?
Okay, I was asking the symbol which was between 2 and x in the first case. That is okay, the example you were showing in the first case. So, okay, what determines how the okay the symbol between x, I mean 2 and x. What's the name of the symbol?
This
Okay, in some languages it's called pipe.
Yeah, in Haskell it's a guard.
Okay, I got okay.
So like
in Elixir they call it pipe operator.
Yeah, it's not a pipe.
Okay.
I don't think. Yeah.
Okay.
I mean, earlier in the book they called it a guard. So
I was taking it literally like from Python, where the determinant is on the right hand side. Where if you say for example, when you're looping.
So yeah, Haskell guards are conditions that restrict the value of the argument.
Okay.
So yeah, at first we were doing like this factorial refactoring where we put the base case up at first. So at first it checks this, it tries to pattern match to that. If it doesn't pattern match to that, then it goes on to this. We can switch. In this case, the order is important, but if we wanted to switch that order around, then it's saying, yeah, so here, if you wanted to reverse the order, you'd have to use a guard. And then in Haskell, guards are conditions that restrict the value of arguments. So here's the guard. And then when a guard is satisfied, Haskell calls on the appropriate function. So if this guard here, if this guard becomes satisfied, then it calls, then it just, yeah, then it does that. But it's kind of, I guess it's kind of being used a little bit differently in list comprehension. Not really sure. Here, if we go over to list comprehension, yeah, we got that symbol again.
So the left-hand side of the symbol is what determines how our final result will look like.
Yeah, exactly.
So that's the point I was missing.
Okay. Yeah, on the left side, we can have, it says you'll see an expression, but we saw, in the next example, we saw a tuple, which I guess there was no expression, but I guess you could think of it as still being an expression. It's just not really doing anything interesting. It's just stating which order it's going to be in. Y is going to be in the first order now. X is going to be in the second order. So it gets switched around. Here we don't do any switching. We keep X and Y in the same order, but now we're going for subtract X.
Yeah. So in that second case, the case I wrote there.
Yeah.
Yeah, so the X will be the first one and then Y will be the second one. Okay, that's where I was confused, but I now get it.
Oh, yeah.
My tuning was in the second X and Y.
Right.
I interchanged them, hoping maybe it will change, but I was wrong.
Okay.
So if I wanted the change, I could have changed the left-hand side, the left side, that is the left side of the operator. So I could have changed such that Y have been y and x times 2. That is
Oh,
to see the
okay.
result. The result I was expecting.
Oh, okay. All right. Do you want to type that up or?
Yeah, I can try it again.
Okay. Okay. While you type it up, I'll be back in like 30 seconds. I'm gonna.
Okay.
Alright, it's time for you don't want to have the color, don't touch it the picture. So your eggs can catch all that stuff. Mine's already breaking this thing. Look. I did. Alright, is this big on the challenge? You don't get to pick your office and how to pick them for.
Times 2. And then, exactly.
All right. I'm back.
So yeah, it gave me exactly what I was expecting. And
Awesome.
yeah, it did.
Okay. Cool. Well, let's move on. So now it's saying we can also compute combinations. Let's say we wanted to find all the possible landing parties of 2 taken from a crew of Kirk, Spock, or McCoy. Oops, one page too many. All right, so here it's saying, so here we could do let crew is equal to Kirk, Spock, and McCoy. And then we'll say, okay, so we want a tuple here, A, B. A is going to get assigned to this list crew, and B is also going to get assigned to that list crew. So we get Kirk, Spock, Kirk, McCoy, Spock, Kirk, Spock. So it's basically iterating. Actually, you're iterating or permutating the list, all the possible combinations that A and B take on, right? So it'd be AA, AB, AA, AB, CD.
There's a permutation.
Yeah. So it's permutating the list. Yeah, I guess I'll type this one up, and then you can type up the next one. So let's see. So we have, we got to use let crew, and then it was a, was it a tuple or it was a list, right? Yeah. So let crew Kirk, and then we got Spock, and it was lexical error in string character literal at the end of the input. Oh, I see what I did wrong. There we go. So crew, all right, crew is that. So now let's build our list. So here we'll have we want A, B, where so collect A and B, where A comma B is, so where A, I don't know, because where A is true and B is true, yeah, so where A is true and B, here we go. And we get the same thing. So just, yeah, permutates through both the lists. That composition almost worked, but did not remove duplicates. All right, so we can add conditions. Okay, so here's the other part. So we've been generating lists, so now it's going to show us how we can add a filter to a list. We can add conditions to filters, the list comprehension like this. So we got AB, we select AB where A is assigned to crew, B is assigned to crew, and here's our filter. So we want to filter all the ones that where A does not equal B, and then we get Kirk Spock, Kirk McCoy, Spock Kirk. So it permutates without any repeats, or permutates without how we would think. These are all the different combinations two people can be assigned, right?
Yeah, without repetition.
So, yeah, without repetition. So that is a little, and then, so yeah, so let's type up this one, and then there's one more example where it shows how order doesn't matter. So, yeah, I guess, do you want to type that up, or?
Let me do it, okay?
Cool. Well, I hadn't been sharing my screen. Oops. So this is what
Okay.
we'll be typing up right here.
Okay. Let me type it.
Okay.
Oh, I'm not sharing my screen now. Mhm. Okay.
Ellie, you covered booby traps and now she has to go to the bathroom. There must have been some magical spell. Yeah, I always got my little thing on them too. Ooh, she likes my food.
Something like that.
Ellie, you can't even know you're going to get in trouble. I'm not going to get in the food. I know supposed to we can go to jail to go to jail.
Oh, you got it. Let me see. Take a look at your screen. So at AB, yeah, awesome. Yeah, so let's try the next one. Let's pick up. We got, yeah, that's pretty. Yeah, where A does not equal to B, so that's that makes sense. So since if A's Kirk and B's Kirk, well, Kirk equals Kirk, so that doesn't satisfy that filter. So it's saying that is a little bit better, but order doesn't matter. So here in our result, we got Kirk and Spock, but then we also got Spock and Kirk. So those are essentially the same combination of two people we could choose. So what we really want is like something like Kirk, Spock, Kirk, McCoy, and then Spock and McCoy. So we just want those three answers. So let's.
So if we introduce a C, then so we'll be having like 3 elements in each tuple, right? Whereby I'll be having all the names in each tuple.
I'm not sure. You want to type it up and explain what you're saying?
Okay, let me do that.
All right.
What in the world is this? It looks like a plate in a really bad mood. That looks worse than my button. And I am in kindergarten. Oh, this obviously didn't work. Yeah, this magic, come alive, change the phone on the count of 5. 1, 2, 3, 4, 5.
So something like this. Okay, A equals is not B and wow. Okay, I was thinking now to make the condition be oopsie. Yeah. I got a result, but not quite what I was expecting. Okay, there. I need to eliminate the third one, whereby.
Yeah, but we only want two people in our final results. We want to see all the combinations. So let's go back to the question. What question are we trying to solve?
Okay, I just introduced a new question. It's okay.
Oh, okay. Yeah. So let's see. Let's say we wanted to find all of the possible landing parties of 2. Yeah, so 2 taken from a crew of Kirk, Spock, or McCoy.
So instead of 2, I was talking of 3.
Oh, okay. So let's see. All right, so the way so it's saying that is a little bit better, but order doesn't matter. For instance, Kirk, Spock core is the same combination of 2 parties that can land. So we want to get rid of these combinations where they're the same, because order doesn't matter. So we want something where we end up with Kirk, Spock in one tuple, Kirk and McCoy in another tuple, and then Spock and McCoy in the third tuple. And then those are the 3 different combinations of the 2 people can land. And so let's say we can do a little bit better by including only the options that appear in sorted order, discarding the rest. And this is how they go about it. They do A where A is less than B. And then they end up with the answer. I'm just going to open up a terminal here and see what we get when we do. A less than B. Because that doesn't intuitively make too much sense to me. Does that make sense to you, or?
So
So we have so let's say we have Kirk here. Is Kirk less than Kirk? It's false. So that won't appear in our final list. Okay, let's say we have Kirk less than Spock. That's true. So we should have Kirk and Spock in our final list. And then let's say is Kirk less than McCoy? And that's false. Oh, I did a capital M. Maybe I should do capital K. So changing it to a capital K, that's true. So we should have Kirk is less than McCoy is true, so that should also appear in our final list. And then if we have Spock is less than Kirk, that's false. Because I guess it looks at the first value. S is not less than K, so yeah, that's false. Is Spock less than McCoy? That's false. And finally, we get down to is McCoy less than Spock? That's true. So by doing the less than, we only get like 3 trues, and then the rest are false. So from this original list up here, where Kirk, so let me present my screen. And so where Kirk is less than Kirk, that's going to be false. Is Kirk less than Spock? Well, K is less than S. That's going to be true. And then Kirk is less than McCoy. That's also going to be true because K is less than M. And then here is Spock less than Kirk. That's going to be false. S is greater than K. Is Spock less than Spock? That's going to be false because they're equal. Is Spock less than McCoy? That's going to be false because S is greater than M. And then we get on to is McCoy less than Kirk? Well, it's going to be false. McCoy less than Spock? That's going to be true because M is less than S. And is McCoy less than McCoy? It's going to be false. So we get 3 trues and the rest are false. So that gives us the final result there. All right.
okay, that will work better when we're dealing with specific strings with where the strings start with letters. But what if okay, I think the first one is better because okay, some place like in this part of the world where when my name starts with O, you'll realize almost everybody's name starts with O when you're a male. So Okot, Otieno, or something of sort. So I think it will not work if that's the case. If it is considering the first letter, that is. I don't know if that's the case. That
it doesn't. I mean, it starts with the first letter, so when it
continues,
and then it continues.
Okay, makes sense.
Yeah. So if the first letter matches, then so let me go back into the interpreter here. Let's try this out. So we got Kirk. Let's say it's Kirk less than Kirkland. Oh, I did a capital. Let me put this as a capital K too. Let's see, is K, so this, I don't know what's going to happen here. Because this runs out and this is longer. So Kirk should be, so this should be true because 4 characters is less than.
Yeah, should be true.
is less than 5 characters, or whatever that is. So true. So now if we do, let's do something else. So if we do Kirk goal, and then if we put an M here, well, M is greater than L, so that should be false.
Okay.
If we do A, then true. Yeah, so that, I don't know. That's kind of a neat way to solve that problem. It's a bit unintuitive, for me at least. That's pretty neat.
I don't know whether it will work in IRB someday, maybe.
What's that?
I don't know whether it will work with IRB too, if that's the case.
IRB?
Yeah, in Ruby.
In Ruby.
Um,
Yeah. And I forget. I haven't used Ruby in so long. I kind of forget how to do it.
yeah, it works. It does the same thing. I didn't know that.
Okay.
I just did some trial.
Yeah, string comparisons in Ruby.
No, if you just put if you put the equal the sign, that is, it will just work fine.
I just do what?
Yeah, it just works exactly like the way. So I guess it's another way of writing the not equals to, that is.
Yeah. Yeah, I don't know, for some reason, I was thinking we could solve it. No, that wouldn't work either. But yes, essentially doing an ordered list generation and excluding all the ones that are equal. Yeah, it's doing an ordered list generation. So then we see on the result here, we get, it does K, S, K, M. Yeah, it does the K first. Well, yeah, so K is less than S, K is less than M, and then here, McCoy is less than Spock. So it's kind of ordered inside the tuple. Yeah. I don't know, did you want to type that up? Or are you good?
Yeah. So I'm typing. Hello?
Yeah.
So what do you want me to type up again?
We can try this. A less than B.
Okay. Okay. Okay, let me do that already. Over something here. I can just change the equal sign.
Know what this means? Detention for oh yes.
I think that will do.
I just love it.
Awesome.
Yeah.
Cool. All right. So let's solve a problem, and then we'll call it quits for the day. So yeah, that is day 1 of Haskell. There's two more days in this book for Haskell, but I think we should get back into the algorithms book, and then it kind of does an interview with Philip Wadler. I don't know. here. Probably an interesting read. I guess he was part of the team that created Haskell. So, yeah, it was the original goal. So we wanted the language to be a foundation for research, suitable for teaching, and up to industrial uses. So basically, they wanted a language for everything. Anyway, let's get over to this question here. And then it fills up the summary of what we learned. So yeah, let's cover this. Haskell is a functional programming language. Its distinguishing characteristic is that it's a pure functional language. So it's not a hybrid language. Doesn't have any objects in it. Doesn't have any other paradigms really in it. It's all functional, purely functional. So a function with the same arguments will always produce the same results. Yeah, that's
isn't that sweet?
that's important. There are no side effects. We spent most of day one covering features you have seen in other languages in the book. And then we went over the basic expressions and data types. There are no mutable variable assignments. We used recursion to define some simple math functions and to deal with lists. And then we worked with basic Haskell expressions and rolled those up into functions. We saw pattern matching and guards. And then we used lists and tuples as the basic collections. And finally, we took a look at building lists that took us into list comprehensions, ranges, and even lazy sequences. And then so let's put some of those ideas into practice. All right, so self-study. We've got some questions here too. So it's want to find the Haskell wiki. So there's a wiki page on Haskell. There's a lot of different compilers you can use for Haskell. So here's some questions. Asking how many different ways can you write this function. Another one is write a function that takes a list and returns the same list in reverse. And then write a function that builds two tuples with all possible combinations of two of the colors black, white, blue, yellow, and red. So kind of similar to what we just did. But note that you should include only one of black, blue, and blue, black. So yeah, kind of the same thing as we just did, more or less. Except we're finding all the possible combinations. Yeah, and then write a list comprehension to build a childhood multiplication table. And then the last one is solve the map coloring problem using Haskell.
I'm sorry.
Are you familiar with the map coloring problem, Okoth?
No, I never heard of it.
All right. Well,
let me take a look.
It is a.
Did you get that recording? As a good teacher,
So right here. So it's the four color. There's a theorem on it, and the four color theorem. So have you seen? You know how maps they have. When you look at a map, let's pull up a map. No, not Google Maps won't have it.
Where are the papers?
that's fine. There we go. I'm gonna mute you for a minute. There we go. All right, so so map coloring problem is basically asking how many colors do we need to color a map so that when you look at the map, no two colors are the same, or no two colors are next to each other. So here's a map of the United States, and when we look at it, we can easily differentiate each region as no two colors are next to each other. This is an interesting problem that I've come across a couple times. It's a let me see what this book says here. Oh, here we go, map coloring problem. So yeah, basically we are given the task of coloring each region either red, green, or blue in such a way that no neighboring regions have the same color. And yeah, there's actually a theorem that says the most colors you need to color any map in a way. I think it was proved to be I think it was proved that you need 4 colors to color any map.
That's at least or at most?
At most, you need 4 colors to color any map so that no two colors end up next to each other. So here for the United States, I think they only need 3 colors. So here they got red, blue, yellow, and red, and no two colors are next to each other. So yeah, so here they're using 4 colors, and yeah, no matter what design you do for any map in the world, or for any for any made up map too, you could all you need is 4 colors, and you can color it in a way that no two colors are next to each other. So the problem that we're given is to write a program that determines which colors are needed for each region. And yeah, it's called the 4 color theorem. The 4 color theorem, or the 4 color map theorem, states that given, yeah, I don't want to read this right now. But yeah, goes into a proof and all that, and it's yeah. So let's see. Says. There we go. Let's use the same idea to do map coloring. So this is in the prologue section. Is where this is where they covered the details of this question. So we want to color a map of the southeastern United States. So right here. So here's the map we're given. So we see Florida, Mississippi, Alabama, Georgia, and Tennessee. So we do not want 2 states of the same color to touch. All right. So here's our guide. So how do you think, so we're given, what are we given to work with? We're given 3 colors, red, green, and blue. So can we write
that what crossed my mind? Maximum would be 3. Small.
Yeah.
Yeah.
Yep. So we're given the colors red, green, and blue. Can we write up a program in Haskell that'll automatically tell us how to solve this problem?
Sure, you can.
All right, go for it. How are we going to solve this problem? What technique are we going to use that we recently learned?
Okay, I would. Okay, I will take the countries as a list. That is.
Okay. Yeah. Let's. Okay, and then we'll do the. Okay. You want to type it up or?
So. So we have. Is my screen shared?
No.
I'm not sure anymore. Let me share it.
Are you chewing something in my class? Spit it out! Spit it out! Spit it out right now! You spit it out! Spit it out!
So that's.
You know what that means? Oh, principal! I have a very bad student.
So we have Florida.
Oh, come on! Dude! I'm not joking. Me either! Dad! Free my esophagus! Wake up!
Which is the state?
Okay.
Another hot day.
Can I just put any, right?
Sure. Well.
This was a collaboration with Onyx Kids.
Well, how are we going to map it? If we put any. I don't know what state. Let me bring up the map so that we know which states are next to each other.
I'm so excited to hang out with the Onyx Kids today. It's gonna be so much fun.
Oh, Florida, Georgia.
Where are they? Here, let me call them. Hello? Hey, are you guys at home? We're here to hang out. Don't come in! Don't come in! Don't fluid is lava! The fluid is lava! Wait, what? Alright, come in. And be careful, guys. Okay, we'll go look for it. There it is! Be careful! Let's climb up! Or we can use the ladder. Whoa! What happened? I can see lava in your house. Wow. That was Shiloh.
Okay, there you go.
Okay, well, it's my fault. Well, I was mining for diamonds downstairs. And it was an accident. And a big one. Flying diamond. Uh-oh.
So.
Stop it. Oh, no, what should we do? How do we get rid of lava? I got an idea. We can buckets to all the lava out of the house.
I'm trying to figure out what to do next.
Okay. Let me help you a little bit. So let's go over here to Haskell. Actually, oh, that's not what I want. So, man, I hate this. Let me present my screen here too. So, all right. So, okay. So here we saw how we could generate lists, and then we learned about list comprehension.
Yeah.
So here we saw how we could like assign something to a variable, 1, 2, 3, and then after that we saw, okay, well, we can bind 1 to X, we can move it into a different position, blah, blah. All right, so here we saw, or we did list comprehension, we can also add conditions and filters. So here we got, so here we created a crew, we got Kirk, Spock, McCoy, and we said, okay, so we're gonna assign crew to A, assign crew to B, and then we'll print out everything where A does not equal to B. Then it gives us that. So this is kind of something we want to build. So our output, we want to say, okay, well, Mississippi can be red, Georgia can be blue, and so we want something output like that, where we got a state, where we have a state and a color. So if we think about how can we build a list that will have that output for us. So if we start off with our variables, so our variables that we want, so our variables that we want assigned to, we want our variables in the end of the list to be assigned a color. So we have our list comprehension here, and then our variable can be like Mississippi. And we got a variable, what was it, Florida. And so this could be like, put this in a tuple, right? So now we want to say, okay, well, Mississippi, so collect Mississippi and Florida, where, let's say, okay, so Mississippi can take on the values, let's say Mississippi can take on the colors, it can take on the colors red or green. And then we'll also do the same thing with Florida. Florida can take on the colors red. Red and green. And then if we do this, if I hit enter here, I get what I want. We got red, 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 green, green, red. All right. So what am I missing here? It's kind of what I want. So we know that. So we know that first position is Mississippi. So red gets assigned to Mississippi. Red gets assigned to Florida. But we don't have any filters, right? So if we add the filters here. And so these are the two possibilities. Well, Mississippi to be red, and Florida has to be green. or Mississippi can be green, and Florida can be red. So we have 2 answers there. And it would also be nice. I think it would also be nice if we had the end result being like stating, well, which state is red. So
we're gonna get extra boost money for this. Are you just going to fucking Sheridan? What? You fucking princess party? I told you to leave it in my room, Derek. Yeah.
But this kind of solves the problem, but doesn't we have to kind of like we have to use our pattern matching ourselves, like, okay, well, red's in the first position, so it belongs to Mississippi. Yeah, let's I don't know, what do you think of both?
Can we use something like a keyword list or something of sort, like a key and a value,
Okay. I think we can do that, yeah. Yeah, that's great. So, are you going to give that a try, or?
It was just an idea.
I think it's a good idea. I think it is a good idea. Maybe we can solve it.
Oh, this is so tiring. Like we've been standing here for an hour. Okay, guys, are you guys ready to go? Of course! We've been waiting for an hour. Mother said 14 hours. Ready, set. Are you guys ready to go? Of course! Yeah, baby! What do you guys want? Happy Meal! Happy Meal! Sorry, you can get okay, you got it. Can we get 4 Happy Meals and...
I was just trying on my time and allowed to write key and value in this case, but I'm getting errors.
Yep, that's all then.
I can't see. Yeah, now I'm having problems seeing. My eyes are small.
Oh.
Yeah.
So like.
Oh, that's a little bit better. Yeah.
So I was trying something like I don't know the structure, how it should look like though. Should be something like maybe key.
Let's see. So if we do. I think this is what you could do.
Good night.
Are you able to see my screen?
Yeah, I can see it.
Okay.
So how can you access 2 in this case if you want the value of 2 exactly?
What's that?
Okay, when you want the value of 2 from this tuple, or what is it? It's like so let me say you want to use the value 2, so you want to pick 2 from the key value thing.
That's child's. This is a real man's game. Are you kidding me?
Oh, yeah. But I guess it's
So
not
now,
really a key value thing, but I guess what I'm thinking is, well, let me use it up in my original example here. So we got
So let me get this straight.
Mississippi, Florida. So what I'm going to do is say, well, okay, so Mississippi is going to be assigned some color, but we want to know what state that belongs to. So in my tuple here, I'm just going to put Mississippi and then comma. And Mississippi is just a string. It's not going to be assigned anything. It's just to help us know that, hey, here's Mississippi, and then it's going to, I'm spelling Mississippi way wrong too. So here's So here's Mississippi, and then after that string Mississippi, we're gonna have our color. It's not really doing anything. It's just there to help us see. And then we get Mississippi red, Florida green, or Mississippi is green and Florida is red. So those same 2 answers, but now it's a little bit easier to parse.
Red plus 2. And I got another yellow plus 2. What's 4? Yeah. Oh, I got another plus 2. What?
okay, makes sense.
No, the twos again, and this time it's about that? I'm sure about that. Yeah, 2 5 plus 2. Hello, fresh start.
Okay, so we say we want our output to be Mississippi, and then whatever Mississippi color is.
Where?
I think I have some good cards. Yeah. One start. Let's just do
Yeah.
this. That, okay? Okay, now, you look over this. Blue 7. And, where do you go? That's 7. On cherry, what do you got? That's right. That means you have to pick it up, Tom. What? That's impossible. You make it before.
Open it up. Mkono. Mguu. Unakuwa.
Yes, boy.
Unataka kuoga baridi?
Sit around again to you, Tom.
Nataka iko na baridi.
No, you know you make it before.
Yeah.
Are you sharing your screen?
No, am I?
No.
What does this mean? It means that I don't have to pick up anything. Okay, no skipping curve.
Best
No
drink.
turnaround. And definitely
Umetoka
no
kucheki
plus 4.
Umetoka.
We're gonna use good old number cards, okay? Yes! Finally! Got more than one color. Yay! Colors now! Oh, I'm sorry, Tom. You need to stop. Okay, first card. I think I'll go first card. 8. Oh wait, another 8. Oh wait, I have another 8. Oh wait, I have another 8. Oh wait, I have another 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. This is my second someone says food before you, that means car.
So
You know. Can I do it? 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 It? Never it. No. I can't be it. I can't be it. You're it. What?
Yes. Wow.
How in the world? Attack someone.
Hey. Unakujanga faster.
Yeah, this is a tough problem to do.
yeah, I realize. So okay, my let me share with you something here.
Yeah, River. Hey, 5 minutes. Yeah, one.
Boys, I have a snack. Ooh, a snack.
You have to mix mine. It's not okay. And mix
In the long run, our data type should the final result should look like something like this, where in this case one will be Mississippi and red, maybe Mississippi and blue, and Mississippi and green.
Oh, I have a nice snack for you.
My only okay.
No, Pat, you're oh man. What? No! Hey, what? No.
So I don't know what I'm thinking here. We have these colors, red, green, and blue. And we want to build a list such that Mississippi gets assigned a color. Mississippi's color. And then Tennessee gets assigned a color, so Tennessee's color would go right here. And Alabama would get assigned a color, and Alabama's color would go right there. And Georgia would get a color, and so forth. Georgia's color would go right there. So that's how we want the end of the. That's how we want our list comprehension to look. So this needs to be in a tuple, right? So in a tuple. And on the right side of the equation, on the right side of the guard, that's where all the magic's gonna happen.
When I am sitting at my desk, you guys remember
On the right side, we want something like, okay, so we want to assign MC, the colors. However, and we also want to assign PC the colors.
54.
Red, green, blue. We also want to assign Alabama's color the colors red, green, blue. We also want to assign Georgia's colors red, green, blue. And then the last one, Florida's colors, we wanted to assign red, green, blue. However, if we look on our map, Florida's next to Georgia, Florida's next to Alabama. So we don't want Florida's color. We don't want it to be equal to, what was it? Georgia and Alabama. We don't want it to be equal to Georgia's color. We don't want Florida's color to be equal to Alabama's color. Right? Florida's next to Georgia and Alabama. And then moving on, we go to Georgia. Georgia's next to Tennessee and Georgia's next to Alabama. So we don't want Georgia's color next to Tennessee's color. We don't want it to be equal to, am I doing that right? Yeah. Tennessee's color. Then we don't want Georgia's color to be equal to Alabama's color. Then moving on, we go to Alabama, where we don't want Alabama. I think we already mentioned that there. Alabama's not to be equal to Georgia's color. Also got Alabama and Florida. So I think Alabama's covered. Gonna get, what's that?
Okay, I was talking about Alabama and Mississippi, and then I realized you're going to Mississippi.
Okay. And so let's go to Mississippi. So we don't want Mississippi next to Alabama or same as Tennessee. So Mississippi's color should not be equal to Tennessee's color, and Mississippi's color should not be equal to Alabama's color. I think that covers all the constraints, right? So these are the constraints we're placing on our list generation. So let's press enter.
I have had enough. I'm not playing anymore. Well, Sasha, I'm gonna play some more.
The Tennessee and
Right.
and the TC. There's no comma between them.
You want?
Okay.
Oh yeah.
In your list, Tennessee up there and
okay. Oh, I see what you're saying. Good catch, man. I get an error and my mind goes blank. Like, what do I do now?
No.
Okay. So here's our. So it looks like it gave us. So that's like input. So okay, right here. So here's one tuple. Here's one possibility. Mississippi. So it's saying red is equal to Mississippi. So if we color Mississippi red, Tennessee is going to be green. So far, so good. Alabama is going to be green. That is not good. Alabama should not be green. So that did not work.
What do you want in your burger? Throw a burger to
So maybe I do need to throw in.
I'm a plain girl, you know.
Are you serious?
I like to
I'm
be
giving you something.
Let me clear this out. Make it a little bit more readable.
It's a meal on this. No, that's perfect.
So if we look at this, so
ketchup, mayonnaise, and cheese, please.
I've got Georgia and Tennessee's color.
All right, buddy.
Yeah, I missed Tennessee's color and Alabama's color. So Tennessee should not be equal to Alabama's color. All right, let's check this out. So saying this is one possibility. Mississippi's red, Tennessee's green, Alabama's blue now. What Mississippi's so red, green, and blue. So far, so good. Red, green, blue, and then Georgia is red and Florida is green. And Georgia is red and Florida is green. So that works. And then it's also giving it gives every single possible combination. So let's say if Mississippi's red, Tennessee's blue, Alabama's green, red, blue, green, and then red, blue, green, red, and blue. So yeah, so that works too. So there's 1, 2, 3, 4, 5, 6, There's like six different ways to color this map with those 3 colors.
I want to lay it down on my burger. I want to do my sesame seeds, but
We are still making food, right?
put the Gucci on this burger. I want Gucci everything.
Yeah, that is a tough problem. I kind of cheated on it, so.
Sprinkle it over my burger. I want Gucci seeds right now. I want to see this dripping.
All right, so I got.
But yeah, this is a problem I've seen a couple times come up in school too. It's a hard problem to solve. However, if you treat the problem, well, the problem is the map coloring problem. It's they call it's a constraint. It's a constraint problem, right? There's these constraints you have to list. So if you treat the problem in that way, then it becomes easier to solve. But if you treat it in other ways, then it becomes very difficult and takes a long time to solve. But treat it as a constraint problem. It's a little bit more easier to solve. Also constraint. So yeah, constraint satisfaction problem is what it's called. So you treat it as a constraint satisfaction problem. It becomes easier to solve, but CSP problems in general, with a lot of variables, they are very time intensive to solve. But here we only had a few variables, so not too bad. Anyways, it's an interesting problem. Constraint. So if you ever see a problem where you got like constraints on it, you gotta like satisfy certain constraints. You can solve it in this kind of way. So yeah. So that's Haskell. So that's or Haskell. That's it wrong today. That is Haskell, and yeah, we won't go into day 2 and day 3. I think we'll wrap up here with day 1, and we'll continue with the algorithms book. I would like to say next week, but I'm not going to be around next week. I won't be able to. I won't be able to hold this mob next week, so we'll meet again in like 2 weeks.
Which topic were we in? I was not there during the last mob, the last lesson.
Okay.
Was it chapter 10? Or did you read chapter 11?
I think it was chapter 8. I thought.
Chapter 8.
Yeah.
We should also go through prologue sometimes if we have time.
That'd be awesome. Yeah.
So prologue is logic based, right?
It is. It is. Do you? I mean, do you want? It's up to you. Do you want to do that next? Do you want to cover that a little bit next, or do you want to go into the algorithms book?
We can do prologue a little.
Okay.
Yeah.
Let's jump into there. It still has a lot more to show you on like Haskell. They go through like higher order functions.
We can finish Haskell first then.
Oh, you want to do all of Haskell?
Yeah.
Yeah. All right. I mean, it's up to you. Cause yeah, we just did day 1, so they still have like day 2. Yeah, 2 more days.
Oh, okay. I think we can just do it all of it.
I'll leave it open. I'll leave it open to cover. We got 2 weeks, so I won't be here next week. So next time we'll meet will be 2 weeks, and yeah, I'll leave it open. Whatever you want to, whatever everyone wants to do, we can do.
I guess next week I'll be leaving the mob alone. I don't think anybody will join. I hope so.
Oh, okay. All right. Yeah, go for it.
Okay.
Yeah, that'd be awesome.
Okay.
Yeah, I don't know. I was every time I start these mobs, I'm like, no one's gonna join today. But yeah, go for it. Start her up, and yeah, sorry, I won't be available next week, but I'll be back in 2 weeks. So cool. Thanks, Okoth.
Okay.
Have a good night.